as well as some of the longer term trends in Chesapeake Bay water quality. So Fei came to work with me directly after completing his undergrad degree from Nanjing University in China in 2015. And then he completed his master's degree at VIMS, working on the impacts of atmospheric deposition of nitrogen on hypoxia. And then now for the past several years, he's been working on his PhD studying coastal acidification. So he's got background both in hypoxia and acidification. And he has received numerous awards and fellowships for his research at VIMS, including the Mid-Atlantic Sea Grant, NOAA, Ocean Acidification Program Graduate Research Fellowship, which has been funding his research for the past several years. So now I'm going to turn this over to Fei. And again, as Susanna said, he's going to give you this two-part presentation. The first half is going to be focused a bit more on acidification in general. And then the second half will be more specific to our model forecast system. And again, it's going to be plenty of time for questions after each of the halves. So send them on in the chat to Fei and I, and we'll do our best to answer them. So take it away, Fei.
Okay, thank you so much, Marjy, for the introduction. Okay. Good evening, everyone. Thank you so much for coming to the presentation today. Just like Marjy said, the presentation will be focusing on two parts, the short-term forecast and also long-term trends of acidification in the Chesapeake Bay. Before I start, I just want to acknowledge the funding sources, and also this work is in collaboration with many great scientists. First, I just want to introduce a little bit more about me. I'm a huge fan of Pokemon game series. You may know this very famous yellow electric rat, which is a mascot of Pokemon. But there are also hundreds of many other Pokemon species introduced to the game series over the past 25 years. For example, in 1999, one Pokemon called Corsola, which is based on coral, was introduced to the game, and it is a water type, which makes sense because coral, they live in the water. However, if we go to 2019, this was recently introduced, and this is also Corsola, but this time it became a ghost type because of the change in water quality, and in reality, we also see lots of events that related to the decrease of coral reefs in the ocean worlds. And this is probably related to increased water temperature and also increased water acidity. So there are many other water quality parameters, such as temperature, salinity, oxygen, and all this related to biology and chemistry in the water. For temperature, an example is that in the figure in the center here, which shows the Chesapeake Bay summer days over the past century. So clearly you can see there is an increasing trend of the summer days in the Chesapeake Bay area, indicating that the summer is we get a longer summer, and also the temperature is increasing. And this increase in air temperature would eventually lead to increase in water temperature, and that may have impact on other biological or physical processes in the water. Another example of water quality is salinity, which is the salt content of the water. The figure on the right here shows the salinity in Chesapeake Bay. For example, in the upper part of the bay where the largest river coming in, the salinity is very low because fresh water has zero salinity. And when we go to the lower part of the bay, connect to the Atlantic Ocean, the salinity can be high, up to like 30 parts per thousand. Why salinity is important? Because different species, they may have different preference for salinity. For example, oysters, they have a larger tolerance of salinity compared to some species of clam. And this is an example of a juvenile striped bass, which prefer the lower salinity range from 0 to 16 parts per thousand. In addition to these different water quality parameters, it is also important to look at the time scales. So time scale matters in water quality study. What I'm showing here is a figure adapted from a recent publication. On the X direction, you see the time in hours. For example, we have shorter time scales like hourly within 1 day, and goes to daily, and even longer time scales on the right direction. And on the y-axis, it shows the relative contribution of the change in water quality. For example, the hourly change or daily change in some water quality parameters can be very high compared to longer time scales. However, these longer time scale changes can have a more permanent impact on the ecosystem. So that's why it is important to study the water quality issues on different time scales. Example for hourly and daily scale is the weather events are like tide, storms, and this will lead to large change in water quality parameters such as temperature, salinity, or other parameters. And this may relate to the impact the shell formation of some calcifying organisms, and also may relate to the development of larvae of some marine species. For the seasonal scale change, an example is the change in salinity. Like in some seasons, salinity can be low, some seasons can be high, and the seasonal change always relate to production. If we go to an even longer time scale, which is decadal scale and century scale, an example of this is the combustion of fossil fuels, which is related to human activities. Another example is sea level rise. Over the past decades, the sea level has been increasing globally. And if we go to even longer time scale, which is geological scale, it can goes up to millions of years. And this longer time scale can impact the evolution of some species. So in our group, we use computer model to study water quality issues. Because computer model is a flexible tool, we can study the issue on different time scales. And today I will focusing on firstly the decadal change of the estification in Chesapeake Bay, and also some daily forecasts of water quality parameters in the Chesapeake Bay. So let's first look at the first part, looking at the primary drivers of Chesapeake Bay acidification over the past 30 years. So what is acidification? The previous speakers already gave a very nice, introduction of acidification. So here I would just briefly talk about this. Acidification, it is an increase in ocean acidity. One of the measurements is using pH. So pH is the negative log scale of the hydrogen ion concentration in the water. So more acidic water means that the water has more hydrogen ion because of its negative log scale. So more hydrogen ion will lead to lower pH. So more acidic water has lower pH. That's one definition of ocean acidification. However, the primary reasons of decreasing pH can be quite different, from across different ecosystems. For example, in open ocean, the decrease in ocean pH is related to the increase in atmospheric carbon dioxide concentration. So more carbon dioxide in the atmosphere can dissolve in water, eventually lead to more hydrogen ion. And the increase in atmospheric carbon dioxide is primarily due to human activities such as like factory, traffics, deforestation. All those can contribute to the increase in air CO2. So in open ocean, increase in atmospheric carbon dioxide lead to increase in hydrogen ion and decrease pH. And that is the primary reason of acidification in open ocean. And we can see that from some observations. For example, what I'm showing here is the atmospheric carbon dioxide concentration in red measured in Hawaii. we can see over the past several decades, air CO2 has been increasing. And the blue line here shows the pH in seawater, which has been reducing over the past several decades. However, if we go to coastal ecosystems such as Chesapeake Bay, the story can be more complicated because of some local influence, such as the river input. So river is a large source of nutrient discharge, freshwater discharge, and sediment coming into the coastal water bodies. And this change in the river input can also impact the acidification in coastal water bodies. So one of my chapters of my dissertation study is to look at how different global and local drivers can contribute to the acidification in the Chesapeake Bay. So global drivers, I mean the increase we see everywhere in the world, such as increase in atmospheric CO2 temperature, and terrestrial driver is the local change coming in from the river. And today I will be focusing on the change in river nutrient input. So in Chesapeake Bay, one of the reasons why we care about the pH and other acidification related parameters is because of the oyster industry. For example, on the figure on the left here shows in brown color shows the oyster grounds. These oyster grounds can provide important critical nursery for some marine species such as juvenile striped bass. And in Virginia, the oyster industry is very important to local economy. So the potential change in the water quality parameters may impact this industry, which could have some impact on local ecosystem and also economy. So the research question for this part is to see what are the relative impacts of global and the terrestrial drivers on Chesapeake Bay acidification. I will just first leave the conclusion here. So over the past 30 years, the primary drivers we have two primary drivers impacting pH in the Chesapeake Bay. The global driver is increased atmospheric CO2, and the terrestrial driver is the reduction in nutrients. You don't have to remember this now. I will go through them in detail very soon. So how do we study different drivers to acidification in the Chesapeake Bay? The method we use is a numerical model. The figure in the center here shows our model grades. So using and different color means the water depth. Warmer color means the water is deeper, and clearly there's a deep trench in the center of the Chesapeake Bay. Using the model, we can divide the bay into lots of small cells and by providing different inputs to the model, we can simulate the physical and biological processes in the Chesapeake Bay. And there are three important inputs. First is the river inputs, such as river nutrient and freshwater sediment. Atmospheric forcing is also important, that include winds, solar radiation, temperature, precipitation, and humidity, all those things. And also here is the boundary of our model, which is in the Atlantic Ocean. So it's also important to tell the model the information along the boundary, which we just use the data from different NOAA cruises. And in the model, we simulate physical processes and also biological chemical processes, and the pH and acidification related parameters are included in the model. As I said, the global driver, the most important global driver contributing to Chesapeake Bay acidification over the past 30 years is the increase in air CO2. So when we increase air CO2, no matter which level in the water, so both in surface and bottom water, we would have more CO2 dissolved in water, and that can contribute to more hydrogen ion and decreased pH. One example from our model results is in a figure here, which shows the change in surface pH over the past 30 years. Warmer color means pH is increasing, and warmer color means pH is increasing, and the cooler color means pH is decreasing. So as you can see, like average from April to September over the past 30 years, pH in the Chesapeake Bay has been decreasing because of the increasing atmospheric carbon dioxide concentration. And this change is similar to what has been observed in open ocean. So over the 30-year period, the decrease in pH is about 0.06 units. Then we can move on to the most important local driver. That is a reduction in nutrient concentration into the bay. So the story is more complicated here. It depends on which region of the bay you are looking at, such as the deep channel, surface and bottom can be different. And in the shallow shoals, the surface and bottom, they usually have the similar response because the water is typically well mixed there. So I will go through this in the next couple of slides. So why do we care about nutrient coming in from the river? Chesapeake Bay is one of the systems that has been nutrient enriched. That means excess nutrient comes in from the river because of the industry, sewage water and fertilizer. Those excess nutrient can fuel the algal bloom. So in the schematic here, the green parts are the algae. So when we have a lot of nutrients, algae will grow in the water. It's just like tree growing on the land. They absorb carbon dioxide and release oxygen. So when we have a lot of nutrients, we would have a lot of algae production, and that will, so they will absorb lots of carbon dioxide. So the carbon dioxide in the water can be, the level can be very low, and they release oxygen. So oxygen can be high in the surface water. The low CO2 in the surface water can lead to relatively high pH. However, the story can be different at the depth because the organic matter produced at the surface layer, they can sink and during this process, bacteria will take over the role. The respiration of this organic matter by bacteria can consume lots of oxygen and release lots of carbon dioxide. So eventually in the bottom water, oxygen can be low and CO2 can be high. The high CO2 lead to a very low pH. So in the deep trench of the Chesapeake Bay, especially in the summer, oxygen level can be very low. And that is also, we call that hypoxia. And yeah, another name is a dead zone. So this can be very stressful to organisms, like if some fish or crabs living closer to the bottom water, this kind of environment is very stressful. So over the past 2 decades, there's lots of efforts to trying to reduce the nutrient coming in from the river, trying to improve the water quality and trying to improve the oxygen level in the Chesapeake Bay, especially at the bottom. Here is an example of the nutrient coming in from the coming into the Chesapeake Bay. I'm showing the total nitrogen input because nitrogen is one of the most important nutrients coming into the bay. From 1985 to 2016, you can see that there's some clearly reduction in the total nitrogen into the bay. And in the future, this change is expected to continue in the future. So once there's less nutrient coming in, which means algae would have less nutrient, so the algal bloom, the production of algae would be smaller. So in the schematic here, we can see fewer green dots here. Because algal bloom is, the algae production is lower, so they use less CO2 and produce less oxygen. So that leaves more CO2 available in the water, and this higher CO2 can lead to some reduction in pH. So if we compare the two cases, nutrient enriched or and decreased nutrient at the surface water, oxygen would be lower, carbon dioxide would be higher, and pH would be lower. Similar as this case, however, now we would have less organic matter at the surface, so the respiration throughout the water column would be smaller. So once we get to the lower part of the water, the oxygen consumption is not that high, so leaving more oxygen available in the water, and CO2 production is not that high, so CO2 production is lower compared to this case. And this lower CO2 is related to some higher pH level in the bottom water. So you may wonder, oh, nutrient reduction is good because it can improve the oxygen level in the bottom water, so organisms may have a better environment. However, you can see that nutrient reduction can also reduce pH at the surface water. It doesn't mean that nutrient reduction is bad. This reduction in pH associated with nutrient reduction just means that the system is returning to a more natural condition. So for example, before the Industrial Revolution, we would have a much lower nutrient level coming in from the river. And back to that time, surface pH would be higher or would be lower compared to the current time because nutrient level is lower back then. So this reduction in pH associated with nutrient reduction just means the system is back to a more natural condition. Doesn't mean that nutrient reduction is a bad thing. We can also look at the change in some shallow shoals like tributaries. In this shallow system, the water is typically well mixed, so we wouldn't have a difference between surface and bottom. So once we have nutrient reduction, pH would decrease in the water column. Just summarize the most important terrestrial driver contributing to the pH reduction in the bay. In the deep channel, at the surface water, we would see smaller pH due to nutrient reduction, and the bottom pH would be increasing. However, in the shallow shoals, no matter in the surface layer or bottom layer, we would see a decrease in pH that is related to nutrient reduction. Example of that is of our model results is showed in the center here. Is the change in nutrient. This is a change in surface pH over the past 30 years due to nutrient reduction and averaged from April to September. Again, you can see some warmer color means that nutrient reduction reduced surface pH. And the magnitude is very close to what we see due to the increase in atmospheric CO2 increase. However, just in the shallow regions like the tributaries, if I plot a similar figure for bottom changes, they are very similar because these shallow systems tend to be more mixed. To summarize this, the first part, so over the past 30 years, primary drivers impacting pH in the Chesapeake Bay, the global driver is increased atmospheric CO2, and the local driver is the reduction in nutrient. Especially in the shallow shell, a reduction in nutrient can decrease pH both in the surface and bottom, but in the deep channel, a reduction in nutrient decrease surface pH but increase bottom pH. This study also has some implications. Like I stressed before, pH reduction associated with decreased nutrient just means that the system is returning to a more natural condition. And organisms such as calcifying organisms, oysters, and other marine species, they are likely facing faster decreasing rate of pH because of both increasing atmospheric CO2 and the reduction in nutrient. Because in the future, nutrient reduction efforts will continue. This will help the bottom low pH and also help increase the bottom oxygen. And at the same time, if the atmospheric CO2 concentration continue increase, we would have a faster pH reduction rate in the Chesapeake Bay or other similar ecosystem like Delaware Bay and the Barnegat Bay. That's why it's very important to control the emission of human-induced CO2 globally. However, if we look at the trend in the CO2 increase over the past several decades, the left figure here shows the atmospheric CO2 concentration, and on the right, it shows the, like every year, what's the increase in air CO2. There's a clear trend that the increasing rate of air CO2 is accelerating. It's getting faster and faster, which is, yeah, that's why it's very important to control the emission of CO2. And at the same time, nutrient reduction will continue in the future and trying to bring the system back to more natural condition. And this will also lead to reduction in pH, especially in surface water. So together, we will likely still see a faster decreasing rate of pH, which also the faster acidification rate in the Chesapeake Bay. And this may have some impact on other marine organisms. So you may wonder, what can we do to help with the change in the future? It's quite complex, but also simple because everyone can contribute to something. And for example, trying to turn off the light if there's no one in the room, that can help to reduce the carbon dioxide emission, and some cleaner way of transportation, and trying to do some recycle. As a scientist, I think it's important to understand more about the acidification or other water quality issues in coastal water bodies. And also those can have some impact on marine species, like the great talks from the previous 2 weeks, from the previous couple of weeks also covered some impact of OA, ocean acidification, on marine species. So keeping studying this impact from OA is also very important, can help with the industry related to aquaculture. And lastly, I just hope in the future, as a game fan, maybe we could see something more like a stronger coral instead of dead coral in the game. And yeah, so this is the end of the first part of the presentation. We would like to take any questions. Thank you.
Thank you, Faye. We'll go ahead and hand it over to Anthony if you've had any questions in the chat box.
Great, thank you. We do have one question so far, but if anyone else has a question, feel free to type it in the chat now. Our first question is from Kathleen, and they ask if all of the various rivers that feed into Chesapeake Bay deliver the same nutrient levels, or how does that vary and how does that affect things in the bay?
Okay, thank you so much for the question. Different rivers, they really have different nutrient concentrations. Like some rivers could have very high concentration, and some rivers tend to have lower concentration. However, river concentration is not the only factor that can impact all other biological processes. It's also important to know the total nitrogen, or total nutrient coming in from the river, which is related to the discharge. That means if we have a very large river, even though the nutrient concentration may not be the largest, the total nitrogen loading coming into the bay can be large. So that can cause some issue. Yeah. So what's the second part of the question? Sorry.
I guess it was just kind of how does that kind of change things for the scope of the bay? You know, does it then affect, say, your pH or hypoxia processes in different regions of the bay?
Okay. Yeah. Like if there's some nutrient reduction in some small rivers, it may not have large impact on pH or oxygen. However, if it's nutrient reduction is, if there's large nutrient reduction in largest river like Susquehanna River, it would definitely have some impact on bottom oxygen, pH, and other parameters in the water. Yeah.
maybe I'll just add one other point there. Also, so for instance, in Delaware Bay, most of the input is just from one river, the Delaware River. And the Chesapeake Bay is complex because we've got all of these, just like the question was, that we have all of these different tributaries. So Susquehanna is the biggest source of water, but the Potomac and the James are big too. So it's a complex system.
Yeah.
Great. That is the only question I see so far. So Faye, you can go ahead and continue. Oh, no, wait, sorry. A couple more questions came in there. So our next question is from Rich, and he asks, are the maps that you showed of the Chesapeake Bay available online in a dynamic format?
It's not in a dynamic format, but it's related to the second part of the presentation, which I'm going to talk very soon. The maps on the website is fixed. It's showing the today or 2 days later, but it's not dynamic. There's no animation on that. But yeah, Marjy, do you have any other things to add to that question?
No, I think you'll talk about more about the maps shortly. So maybe we can follow up and address that after the second part. I do have another question here. It says, can you and either this is says, can you address how the Chesapeake Bay health has been affected by the relatively recent coordinated environmental efforts, money devoted to cleaning up the bay by states whose waters contribute to the bay? Do you want me to take that, or do you want to take that?
Yeah, you can take that.
So there's been a huge effort for and money poured into nutrient reductions across all the states that in the Chesapeake Bay watershed, and we're really beginning to see some real improvements in water quality. So in particular, the focus has been in particular has been focused more on hypoxia so far. So acidification has kind of come up more recently as a critical issue in the bay, and it's difficult to that's one of our another something that we work on a lot, is trying to see how big the improvement has been. And it's really complicated by the fact that these some years are particularly wet and they just bring in more nutrients. So it's hard, we see we have this long-term trend of decreased nutrient concentrations in all the rivers. But if you get a really stormy, wet year, you've got a huge amount. So it's really difficult, and you take a lot of data and a lot of models and a lot of assumptions to try to tease apart how much the bay is seeing an improvement due to those nutrient reductions. But we think that the evidence is showing that we can really quantitatively see the improvement now. So it's very exciting.
Great, thanks,
I
Marjy.
have one more question here kind of related to that from Christine, who asks if the nutrient reductions have been influenced by less fertilizer usage by farmers upriver.
Yes, absolutely. Definitely. We've been working on nutrient reductions for the past 30 or so years. Some of the easiest nutrient reduction efforts were to stop wastewater treatment plants. And so that was kind of the lowest hanging fruit. And that was the first thing that was really tackled. Reducing fertilizer input is a much more difficult, much more broad scale. It's a more difficult problem, but it definitely, they've been working hard on it to work with farmers in the Susquehanna and Pennsylvania. And we think that that's really a reason that we're seeing the success in the bay as we are, is because of that reduced fertilizer input, among other things.
Yeah, and just another thing is just like in the figure here, agriculture is mostly due to fertilizer. So yeah,
Yes.
that decreased over the past 10 years, but the goal for 2025 is trying to decrease that agriculture part of nutrients.
Okay, I have another question here from Beverly who asks, since the James is so close to the mouth of the bay, will it have any more or less effect on the bay with the in and outgoing seawater?
Yeah, in terms of like hypoxia or the impact on the bay, pH or acidification, other parameters, I think James River have a small impact on the main channel because it's, like you said, in the very lower part of bay and very close to the Atlantic Ocean. Yeah.
Okay, great. That is the last question I see so far, so feel free to continue.
Thank you, Anthony. Okay. Yeah, so the second part of the talk will be introducing the short-term water quality forecast in the Chesapeake Bay, which is developed by Marjy's group. I just paste the link to our forecast system. So if you click the link, you can go to the website and check that. And I will also go over some slides talking about the forecasting system. So there's just some introduction on the forecast. I think one forecast that's very important to our daily life is weather forecast. So you may check that every day. One of them is the hurricane forecast, which can be very helpful because this kind of forecast can help people make decisions and try to move maybe to a safer place, try to avoid the damage potentially caused by hurricane. An example is this hurricane forecast, Hurricane Irma in 2017. So yeah, using the models can project the potential trajectory of the hurricane. And today, I will talk about the short-term water quality forecast in the Chesapeake Bay. So the water quality forecast, because different marine species, they may have different tolerance, preference for toward the different water quality parameters. So one of the goal of this forecasting system is to provide the information that may be useful for you to use them to make decisions, such as where to fishing or to the hatchery folks if there's some maybe some change in the salinity or acidification related parameters. So this forecasting system is based on the same model I introduced briefly in the first part. The difference is that the atmospheric forcing is using the NOAA atmospheric forcing, which is for the weather forecast. So we use those information and also the river input from like USGS, United States Geological Survey, and using all this information to forecast the water quality in the bay. Before getting the forecast products, one important step is to evaluate the model performance by comparing the model results with observations. So in our group, we have extensively evaluated the model performance and calibrate the model using long-term historical data such as temperature, salinity, oxygen, and other parameters collected in the bay. And on the other hand, we over the past couple of years, we also because of the development of the ocean acidification forecast, we also compared to some high quality recently collected carbon system data, such as total inorganic carbon alkalinity and also pH from one of the collaborators, Elizabeth Chadwick. And also there's some new data coming in some hatcheries in the Virginia tributaries. So the more we, so it's always useful to get more data to compare with model to make sure that the model is working properly and also improving the model performance. After the evaluation, we can use this system to make some forecasting products. here is a screenshot from my phone. You can also use type the link to your phone, and you can check this anytime on your phone if you want. There are different menus here, including hypoxia, and also different plots of hypoxia oxygen level in the bay, and also salinity, temperature, and some maps focus more on the tributaries of the bay and other parameters related to acidification. So here I want to give a brief introduction of the history of this forecasting system. On the website, we now have nowcast, which is the water quality condition for today, and 2-day forecast, and that is a condition in 2 days later. And those information is produced automatically every night. So every morning will be up, you can see the new information. And hypoxia, oxygen, which is oxygen, and salinity temperature information has been posted on the website since January 2016. And acidification related metrics such as alkalinity, pH, and aragonite saturation state, they were added to the website at December 2018. And over the past 2 years, we've already introduced this system to different stakeholders and tried to get their feedback and trying to improve the forecasting system so the information can be tailored more to their specific needs. And today, if you have any feedback or if there's anything you want to see on this forecasting system, please let us know. We would be more than happy to take any feedback from you. And the next couple of slides, I will just give some examples of the forecasting system. Figure on the left here shows the nowcast of, which is a screenshot got from 2017, July the 28th. Because in the summer, we can see low oxygen in the bottom water of the Chesapeake Bay. I will show the comparison of the current time later in the next couple of slides. So in the summer, you can see that there's a large range in oxygen. Blue color means oxygen level is high, means it is good bottom water, and marine species such as bottom fish and crabs, they may likely live in this region. However, if you go to like yellow region, oxygen level would be lower. You may see fewer fish or crabs. If you go to the red region, oxygen level can be very low. Sometimes it can be lower than 1 milligram per liter. And in this very low oxygen region, it is, so it's very stressful to marine organisms, so they may not live in there. And on the website, there's also other information such as 2-day forecast. This is a 2-day forecast grabbed from the same day. So you can see after 2 days, the oxygen level can be different. In the main channel, the low oxygen region seems to be smaller. And more clear way to see that is a clearer way to see the difference between these two. That is a forecasted trend over 2 days. If the color is blue, means the oxygen level will increase, and if it's red, means oxygen will decrease. Yeah, so for that day, oxygen level is projected to increase in the most part of the main channel. If we look at the same figure for today, this is what I grabbed earlier today, because now oxygen level is high in both surface and bottom water. So you can see oxygen level is like over 9 milligram per liter, which is high compared to the summer months. And we don't see much change over the next 2 days in terms of oxygen. On the website, there are also other types of figures might be interested to you. One of them is the profile, the depth profile. So we included 4 different stations in the bay, so the first 3 stations in the summer usually see hypoxia, and the CB 7.1, the southernmost station, which is shallower, the water depth is shallower. So you can see the depth profile here. On the y direction, it is the depth of water. If we, for example, from surface to bottom, oxygen level usually goes down in the summer months. And CB 7.1, it's on the shallow show, so you can see that the water depth is smaller compared to other 3 stations, and oxygen level is not that low near the bottom. Another type of figures is the time series. Similar 4 stations, I just use 2 stations as an example. So you can see the how the oxygen level evolve over time. The green line is the model results, and on top of that, the gray circles are the in situ observation of oxygen level. We can see that the model can simulate the oxygen level very well. And the black line in the center here, it is the long-term average of the observed oxygen. So, and on the figure, you can see where we are now. In early March, the oxygen level is still high, but as it is very likely that in the next couple of months, oxygen level will be very low, especially when we go to the summer. As I said, there are many other parameters such as temperature, salinity. Here is an example of temperature grabbed from today's forecast. In the next 2 days, temperature will likely increase. So that's also, you can see that from your phone that temperature would be higher in the next 2 days, but next week temperature will be lower. So if you want to come back and check our website, maybe next week the temperature will be lower and you would see some decreasing trend in temperature. Here is an example of salinity, lower salinity in the upper bay in the tributaries and the higher salinity in the southern bay connect to Atlantic Ocean. And you can also see the change in salinity over 2 days. This information will also be available in another platform on the Maricruz website. It is being developed, and where you can zoom into the map and see, just zoom into the map like if you use Google Map, just similar to that. So more information will be added to this website. Over the past 2 years, some big efforts was trying to including the ocean acidification related parameters to the forecasting system, including pH, alkalinity, other variables. What you are seeing here is the example, the forecast of surface pH. So pH is lower in the tributary because freshwater always have lower pH. It's around 7, and in the ocean, pH can be higher. It's around 8. And this, from here, you can see that the forecasted pH trend at surface can be high. Like the numbers can be like 0.2 units. If you remember the long-term trend I talked about in the first part, those long-term trends is around 0.12 in the surface water, which is not large compared to the day-to-day change. However, those long-term change may have a more permanent impact on marine organisms. Another example is if you can also download the outputs. If you want to download the outputs, you can plot the figures by yourself. Here, I just grabbed some outputs from the model forecast and plot the difference in bottom pH before and after a hurricane. So before the hurricane, you can see pH is like this, and after the hurricane, we can see the difference. So at the surface, oh, this is bottom, sorry. So bottom pH will be higher after the hurricane in some deep channel here. This is because in the summer, even in September, bottom pH can be very low because of the lots of production going on at the surface water. And once the goes to the bottom water, a lot of oxygen is consumed and produce lots of CO2, making pH lower. However, once hurricane comes to the system, it can mix the surface water with bottom water. So surface water tend to have higher pH and bottom water has lower pH. By mixing during the hurricane, the bottom pH can be lower, or can be higher, sorry. And another figures, including the focus map of the Virginia tributaries, because some hatcheries, they are interested to see these focus maps because they want to know, like, if my hatchery is here or here. However, if you zoom into this, so we have this focus map on the website. However, if you zoom into, you could see the each grid cell, and sometimes in the small creeks, our model doesn't have high enough resolution to cover those regions. So the next couple, our current work is to trying to improve the model horizontal resolution and can cover the small features in the tributaries. An example is here showing, so on the left is the model grids we used in our current forecasting system. And in the summer, we'll be switching over to this higher resolution model. You can see this higher resolution model can get the true depth information in most areas. And in some small creeks, we also can have the coverage there. So current efforts is to evaluating the model with data, and yeah, they will be available in the summer this year. Just a quick animation showing the high resolution model. Here is showing the surface salinity. So like in a small creeks, you can see that this new high resolution model can cover those regions, and also in the eastern shore, on the eastern shore here. Another effort is to focusing on the even smaller scale. That's the tributaries in the Virginia portion of the bay. Two tributaries, the York River, Rappahannock River, and a little bit of the Potomac River here. So you can see from this current version to this new version, which has 120 meter resolution. That is very high. So if you want to go fishing in some smaller like creeks, you could also check this information once we fully evaluate the model and yeah, post that online. Yeah, and also for some hatcheries, they may located in some smaller creeks, so this can be very, very helpful for them as well. And here is a quick animation showing the surface salinity. Yeah, very small details can be covered in this higher resolution York River model. So that's all the introduction about the forecasting system, and we would like to have your feedback. Like if you have any other information you want to know or you want to see on the forecasting system on the website, please let Marjy or me know. Yeah, and now we'd like to take any questions. I can, yeah.
Thanks so much, Faye. That was great. Anthony, have we got anything from the floor?
Yeah, we have one more question that's come in so far. That question is from Edward. He says, most of the weather system forecasting is based on tracking the changes in density of air. So are there any oceanic studies that are based on the density of water?
So if we have salinity and temperature information, it is also easy to add density onto the website. So density is always calculated from temperature, salinity. So if you need that information, I think that's possible to have density on the forecasting system.
And I'll just also add that yes, so the model includes density, and that just like the atmospheric models, density is absolutely critical. The water density. So this what Faye is showing is absolutely taking that into account, and the dense salty water coming in from the ocean goes in at the bottom, and then the fresh surface water from the rivers comes out at the surface. So just like the atmosphere, the model is the motion of the water in the bay is all driven by those density gradients, just like in the atmosphere. So yeah.
All right, I don't see any other questions.
If there's no other question, maybe I can quickly go over the website. Can I? Is that it?
Yeah.
Okay.
And we would be very interested to hear, how you might use some of this information. Do you want to click on the depth to low oxygen for a moment? This is something that from a previous outreach, that another event that we held, we found that some of the feedback was that fishermen wanted to know how deep they could fish to before they reach that hypoxic zone at the bottom. So if you scroll up, Faye, here there are 4 columns. And so these are at the 4 stations on the map above. And basically they're all blue now. This shows that you can fish all the way down to the bottom. The bottom water the bottom sediment is shown in brown here. So when you look at this in the summer though, it'd be much more interesting. And there'll be the bottom, sometimes up to about 20 meters of water will just be red. So fishermen were saying they wanted to know how deep they could fish. And so we put, in response to that, we put this up here so that they know if they're near this spot on the map, then they can only go down and fish in the top 20 meters or so. So that was just an example. If if any of you see a way you could use any of this, the salinity, temperature, oxygen, and then acidification forecast, we would love to hear how you might use it, or again, any suggestions for other ways to provide the information.
Yep, and there's also contact information on the website here. It's Marjy's email, and and also here have some the size of the dead zone in different years. It's like a report card, so you can check out the volume of hypoxic water in a bay.
Did have another question come in from Mark. He said it's a very interesting model and forecasting tool. How do you collect data on the small tributaries, and do you need assistance in collecting that data?
So our group, we don't collect data. So there are some data available in the hatcheries. So they also shared some data with us. Those are typically in the smaller creeks, and that can be helpful for us to comparing with the model. And recently there are a couple mooring stations added to those hatchery sites in the Virginia portion of the bay. Yeah.
And we will, yes, we're always interested in more data. That's what really drives the model. So the more data we have, the better the model is. And so, yeah, it's the main part of the bay is very well sampled from the bay program. And then as you get into the tributaries, things change really quickly on small time and space scales. And so it's really important to have a lot of data. So yeah, all data streams are appreciated. And we have Emily Revest, who spoke last week, has given us some, she's got a citizen science program where she gets data from sometimes from landowners along the water. And so we have that to use as well. So variety of different types of data.
Are there any other questions?
None that I see.
Okay, I'm checking the chat box. We'll give folks another minute or so. And I'm going to go ahead and share my screen again so you guys can see those links and mark them. Of course, they'll be with the recording as well. Okay, and one more thing I'm going to show our audience. If I can get the PowerPoint to work. Is one final reminder with our big take-home messages. And these are all ways that you can help reduce our impact and lower the impact of ocean acidification. First is by reducing your nutrient runoff, by decreasing fertilizer usage on your lawns and gardens and adding native vegetation buffers. You can also save electricity by switching to LED light bulbs and using Energy Star appliances. You can take what you've learned from tonight and any of the other talks that you've participated in and teach your family and friends about acidification and the ways that they can help. And finally, you can take advantage of mass transit opportunities in your area, or if you're able to, choose a more fuel efficient vehicle or use you walk or ride a bicycle. And these are all small ways that each of us can help. And so with that said, I'll take the opportunity to say thank you. I see one more chat. Anthony, we got one more?
Yeah, we had a question come in from Paul who asks, with the nutrient levels entering the bay showing a decline, does this bode well for striped bass reproduction?
I would, it's a tough question. I guess I would say it's complicated. Susanna may be able to you have your, probably have something to say on this lines. But there's a lot of stressors. It depends on lots of other management, fisheries management activities as well. I don't know, do you have anything to add, Susanna?
Or I wish it were that straightforward. One of the things we'd love to get more data about are the tributaries, the spawning tributaries, because we know that things like acidification have a big impact on the development and success of these spawning stock. And when you have these big rainfall events in areas that have strong water flow, it can have an impact on larval development. And it's really complicated. So I'm afraid I agree with Marjy and Faye. It's not just a simple answer. I wish it were that simple. It's even more reason to get more data about ocean acidification and dig deep into it. But there is promising information. I think a lot more attention is being focused on striped bass in the Chesapeake Bay and other areas right now with management. And there have been a lot of changes in fishery management just in the last year in Virginia, and hopefully it'll be reflected in other states that share in the same stock too.
One way to think of it maybe is what, as Faye was saying, is that we're returning with a reduced amount of nutrient runoff. We're making the bay return to its original, more helping it move towards its original condition and the natural condition of the bay, which, you know, we've got to think is the right way to go and should eventually help striped bass as well. But it is complicated.
Hopefully that answered that question. Anthony, anything else?
No, that's everything.
Okay, well, I want to take the opportunity to say a huge thank you to Faye and Marjy for your willingness to share your data with our stakeholders and as part of this group of talks. And we've had wonderful participation. I don't want anybody to go anywhere because it's time for us to turn the floor over to Kirsten with our raffle. So I'm going to stop sharing and ask Kirsten to take over.
Thank you, Susanna. I think this is one of our favorite parts of the evening as well after all these wonderful talks. Just to say thank you for participating and for hanging with us through these 4 sessions. And tonight's raffle prize is a $25 gift card to Bass Pro Shops that's sponsored and donated from Maricos. So we're going to go ahead and give the wheel a spin and see who won. Terrific. So tonight's winner is Elizabeth Lang. Elizabeth will be in touch by email to get you your gift card later this week. So thank you so much for coming out tonight. And I just have a couple of quick comments to close out our Hooked on Ocean Acidification program. So I'll share those with you. And Susanna, do you want to pop that slide back up with contact information just so people have it to refer to?
Absolutely.
Thank you. So on behalf of Maricos and Maycan and all of our partners in the Hooked on Ocean Acidification program, we'd like to thank you for sharing your evenings with us over the past month. Our series launched with Dr. Grace Sabah's regional take on the causes of ocean acidification, the rate of change our oceans have experienced and what we can anticipate in the future, and also provided some examples of observation networks and policy initiatives in New Jersey and at a regional level. As Dr. Hans Baumann highlighted in his presentation on the vulnerability of coastal fishes, ocean acidification is a concern for our regional fisheries, especially for early life stages and in conjunction with other stressors like rising water temperatures. But we shouldn't walk away with this gloom and doom perspective. There is a lot of research yet to be done on both fish and shellfish. The differences in pH thresholds for oysters and the valuable role seagrass beds play in buffering the Chesapeake Bay's water chemistry were illustrated in Dr. Rybest's presentation last week. And we hope you'll continue to follow her research into whether seagrass plantings can be used to mitigate the effects of acidification and reef restoration projects. And then tonight, Faye Da and Dr. Marjy Friedrichs wrapped up our educational series with their investigations into the processes that influence acidification and hypoxia in nearshore waters of the Chesapeake Bay. Perhaps their mobile-friendly forecasting tools might just help you plan your next fishing trip. So as Hooked on OA concludes, we hope you'll take away some ideas on how you can help reduce the effects of acidification in the waters where you fish and recreate, and share what you've learned with friends, family, and others in the fishing community. And if you'd like to hear about state-led ocean acidification action planning initiatives, Maycan's April webinar will focus on efforts being undertaken in Maryland and New Jersey, as well as at a national level. And you can find more about that on our website at midacan.org. So what's next for Hooked on OA? Well, we'll be sending out a questionnaire by email in the next week, and we'd love to hear your feedback or additional questions you may still have. Certificates of completion will also be mailed out to those who attended all 4 evenings. And we thank you again for joining us to get hooked on OA, and everybody have a great evening. Thank you.